is a single, I mean, if the sinusoidal function, so n cannot equal to 0, right?
So
we
that you
start
have
from
to
one.
check.
I need to double check, I understand. But do you have the textbook? The problem, I don't remember the problem.
I have
No,
question.
okay, I just want to make sure. This one, we do not have a formula of this. Or we have the formula of this.
The question is here, and the question is you corrected.
Yeah, you see here, that's what I mentioned. This is a infinite square bill, right?
Yeah.
And n start from 1, not from 0.
Oh, so that you
That
have
is,
corrected.
yeah, I think that is what I correct. You see that n equal to 0 is
0.
0,
Yeah.
and also the solution n equal to 0 is
Yeah.
not accepted.
Yeah.
Yeah, I think that is happening in textbook.
Yeah.
Yeah.
So I have done by using this formula, by using this
Mhm.
wave function,
Mhm.
and I just this morning saw in Blackboard this function,
Mhm.
and so I need to do again putting this function, or can I
Yeah.
submit by this one?
I remember if I use this one, you probably the probability of something is not correct.
Probability is yeah. First time I got a 0, and that n equal to here.
N equal to 0 is 0.
And 0, and yeah, this is physically not acceptable, but
Right, so that's can you
mathematically-
do again? With
Okay,
sorry.
I will do
Yeah.
I will do it again.
Yeah, okay. That I remember there's some pattern in this textbook.
That day I was late in class, and
Okay. Let me also double check again, go back to my office. If everything's okay, I will not email you.
check in Blackboard. I can check. But I checked accidentally. Yeah. I know.
You are lucky.
And
That is why each time really use some of formula or something, we need to know where it come from, right? So either it is correct. Because if the pattern is, I think maybe this, sorry, I'm dirty, it's 10:30, thank you. I'm fine, thank you very much. So we need to double check ourselves. Even I forgot to mention that you see a lot of pattern here. And we need to judge ourselves, see whether it is correct or not.
okay.
Okay. All right, see you then.
On the weekend, you can study together on weekend in the weekend or no? In the weekend, study together or no?
We
Yeah.
we stay with
Or
Bimal, you know Bimal? House.
in house, study in house.
Yeah.
I have in my building study room. You can come from my house and study together in weekend because in school I didn't have card for parking. I buy for lecture for the time lecture. In the weekend, you want come and what's the name?
Where? Jacob.
Yeah, Jacob. Yeah, I sent message to him.
I think Jacob is
When you
planning
want
to
to
study
study
in the week.
in weekend, yeah, Sunday or Saturday, no problem. The
I'm
morning,
still
yeah,
thinking of staying
The morning, no
because
problem.
today to like kind of have a
study together.
Stay together.
Yeah, for ready for exam because I think it's very difficult.
Sure, sure.
I live here, the Marshall building, you know.
No, I don't.
Here, the high building after this street.
This is oh, I never go. This is our from there, from the stop. And this
My building here, the after the fourth street.
That's one. Why should we do this is for my.
Live in the clubhouse.
I live in UK. UK.
Where?
This one. I live in
Okay.
AN segment and where should we use instead of AN segment? This one.
Here.
It's in South Preston Street.
I don't know.
Yeah.
I live here, third year, but I don't know.
It
Okay.
takes
More
15 minutes
minutes.
to me to reach
Okay.
my place by walking.
This one we used to develop the series.
Yeah.
Okay.
And in,
Or meet here in the
we
college.
we do not have here
Open
we do
the
not have
weekend or not?
that.
But I
Formula
think
year.
I can, right? Because I pay for graduate.
Yeah, we have
Ah.
to.
Here? Welcome go.
Signal too,
Yeah, I know.
and AN signal.
I think this part is very difficult.
This is the same thing, right?
This one.
No.
Like you are
Yeah.
asking.
AN signal, right signal.
I study
Yeah.
more,
Yeah.
but when you
But
see
good question.
the
Yeah.
people
This one, there was a segment and segment. I don't know. You take
in
up
the
that one.
open, I
I noticed one.
Close to here.
Okay, it was in the book.
Got
Then you can consider it. When I not equals one, it was there. Okay.
good. Question in math. Homework for first question. Very brilliant in math. Homework for first in math.
Ah.
Very good. Homework for this one. Mathematical.
Jacob.
Is there one?
Oh, yeah, sure.
Oh. Homework for return just get written yesterday.
You said you did, right?
I have secured.
You got the
test one. I got the wrong in that
I don't know
that derivative
the
method.
name.
Is he written?
Please,
Yeah.
To yesterday, to mailbox?
No,
Yes.
in person.
That's Jeremiah.
Yesterday, what?
Last class. Yes, me. Yesterday.
Oh, yeah, I have that.
You want?
Okay. You mean that one?
Okay,
How about
thank you.
Yeah.
Oh,
you mean this side? I think I have to go down.
You ready for this presentation, Mayor?
Oh,
They're going to that?
Oh, yeah. Are you giving it?
Yeah, I'm gonna try to go.
You want the first one or first one?
Let's see how hungry I am.
Yeah.
This one?
Yeah. I brought food just in case. I just went outside
This
to
fifth.
ball a chicken sandwich. Like,
There you go. Ready to go. You're ready for anything now.
PhD or?
now I'm about to have some caffeine.
You know Melinda?
Perfect.
Melinda from
You're
Ferenc.
so kind to your body.
Ferenc.
Well, this is like the one day of the semester that I've been working.
I work in
I heard about.
I'm so tired. I sleep.
Which question?
Ah,
is
good.
it? I have the name,
I
Yeah.
don't know.
but I
don't
don't
know.
I feel like less sleep is more now.
He worked in
Like when you do get good quality sleep, it's like, oh my goodness. It's a whole new world.
near
Oh,
That's
Crawford.
first question.
But if you sleep all the time, then it's like, you kind of need that much.
Near
What
Crawford.
was the? I have done. Okay. Third question is
Let's give him the talk later.
Yeah.
I don't know his name. It's supposed to be like on gravitational
Oh, okay,
waves,
okay. Yeah.
black holes. I know the topic, not the
I
name.
work,
Yeah.
I work with
The guy from Vanderbilt.
in the lab 1 year and
Cool.
Sounds pretty interesting.
3 years.
It's at the planetarium, right?
With Dr.
Is it like a big giant room, or is it like?
I finished for all class,
Planetarium?
but
I don't know how they're gonna give the talk.
again, the
'cause it's
study
like-
for this month
it's like a bunch of
and,
seating,
the next,
then-
semester,
I think there's like a little
I
stage in
again
the front.
study-
But
Okay. I've
they're
never
enormous
watched the
seats.
building.
I'm having a pretty bad headache.
The planetarium's pretty cool. Have you ever been there?
No. I haven't-
Not,
I haven't been there.
Yeah, I took my daughter one time. Yeah, like they'll like show the thing up the top, like you can like tip the seats back, and they'll like do like a presentation. It's like a theater
Yeah.
kind of.
Yeah,
So the theme was like the planets and stuff. So like it went around, like flew around all the planets and stuff. Kind of cool. I don't know. Different.
Yeah. I've sat. We had a planetarium in my undergrad.
Came
and
here after
I don't know if it's anything like this one on
Here?
campus.
Maybe
It's on campus,
continue
right?
this one.
Yeah.
Okay.
No,
Right
no,
by
I'm
School of
asking,
Business.
In your country,
Yeah.
you finish
How do you
your
get there?
undergrad
Is it like kind of walking
Yeah,
to the
my
BAV,
country? Yeah, yeah.
or is it?
and
And continue
You know where the
with
BAB is?
master and PhD.
It's not close to there.
That's
PhD not sure,
No.
but when I want
They
7 years,
go away.
I take it
Cross
all
campus.
course.
Or not.
No.
I drove.
Yeah.
I drove around it when I first came over here. I was like,
Yeah,
is this a science building? I'm like, I don't think so. But like,
Yeah,
I like
you definitely have to be
know what it looks like.
strategic, and there are sometimes
No,
writing
no.
equations so big, and I'm just like,
No,
maybe.
try.
that one's not getting down.
Because no,
You want a protein bar? Like, I have. It's like peanut butter.
first one had exam.
Are you sure?
I'll probably need real food.
We had
Oh no,
Oh,
just.
no. I think this
What's real
October.
food?
It's really-
within 1
After
week.
2 months or 1 month.
Just imagine it. It's probably.
They said within this week.
I know a few students were asking
Right,
if there's
exactly.
gonna be an
I know.
exam at the like end of class.
You
I guess we
for
can
the
ask
quarter,
them.
like-
We probably use a meal today sometime.
I heard it was
Maybe.
like 2 or 3
Or
people
this
talking
week.
about it. I don't remember if you were one of them. And I was gonna ask if you
Oh,
But
remember what's gonna be on the exam. It's gonna be the derivative method.
Yeah.
The series method's not gonna be on there, right?
Quantum mechanics.
series method?
The series method's not gonna be on
Hopefully.
No.
What's the?
Derivative, approximate,
Oh,
green function, and integration. Partial.
611, yeah.
Very strong man in math. Partial. She can help you.
Thank you.
We can study together.
Okay, on the weekend you can make all students no problem. But where here or the outside? Sometimes I can't here because I don't have car for parking.
I wonder if it's free on the weekends.
Okay, you can.
Yeah.
Oh.
Yeah, look for signs.
Yeah. Because I remember, because I told either you, because I told you the first day. I was like, oh yeah, after like 4. It's like,
Go to the parking lot like today, and if you look,
I'll take a picture of it. I'll
okay,
flip out.
you send it.
Oh yeah.
There's a sign that tells you exactly when parking is free and when it's not.
No, I want for 2 hours or 2:45 minutes.
Yeah. I think after like 4 p.m. Parking is okay. For a second.
No, I'm fine. Thank you.
So this bullet lecture at 7 o'clock, you wanted to attend, and just want to mention that.
Are you going there? Or
What?
are you going there?
I'll go, yeah, I'll go, yeah.
Okay, because I haven't been to
Yeah.
planetarium yet. So.
Yeah, lunch, it's just, yeah, it's nice.
Okay.
And also he'll give a colloquium, I think, tomorrow at 3 p.m. That may be a little bit higher standard, this public lecture,
Mhm.
so it may be at a little bit lower standard.
Is it at the planetarium still?
Planetarium, yeah.
Tomorrow as well?
No, tomorrow will be natural science 112.
112?
All right, let's get started. So what I want to do is just Fourier series today so that you can solve PGE problems, especially in Cartesian coordinates, right? I forgot to give the problem because I thought I'd finish Fourier series and then give you the problem because you may need to know something about it. As I said, if a function is periodic, what we mean by this is it repeats itself, right? I mean, at some interval. Okay. N equal 1 is a fundamental thing. It can keep repeating, right? So if it is periodic, we can write the Fourier series expansion of the function. That's the simplest condition, right? I mean, so we can write f of x as combination sine and cosine series. Okay, these are called as Fourier coefficients. So this is a real, this is a Fourier series in real, the coefficients are real here, a n and b n, but you can also have a complex representation of the Fourier series. All right, so the Dirichlet condition, as I said, I mean, this is the obvious case. If it's periodic, yes, you can do that. So if it's periodic, this is what it means. If f of x is periodic, then one can have Fourier series representation. And I also justified a little bit, saying any function can be written as part sum of even and odd function, right? And that's why cosine and sine is you can understand based on that also. So in general, if f of x is continuous, yes, you can do it. But if f of x has a finite number of discontinuities, you still can have Fourier series representation. Provided, integral of f of x dx is finite, okay, it doesn't blow off. Right? So last time you were asking why this modulus sign, right? The main reason it's coming from is because this can also be Fourier series, f of x can be written in terms of exponential of I 2 pi n x over n. Okay, that's the reason you put when you have that, there are two conditions. One is called, it converges this one, or square integrability, we call it modulus of f of x squared dx. And for Fourier transform to exist, that is the condition. But for Fourier series, even modulus of f of x dx is finite, that's enough. I mean, that's what usually I come up with. Some people give in terms of, for the Fourier series to converge to represent to the actual function, they will write it in terms of how the a of n and b of n real those coefficient decays as a function of n. Okay, if it decays the power law or 1 over n, or if it is constant, based on that. So, but all those things are all buried in this particular one statement. Whatever it is, this has to be, if you give it this representation, this has to be finite. This integer over a period must be finite. So even though the function may have some discontinuities, if this condition is satisfied, you can have it. And if function is oscillating, that it can only have finite number of minima or maxima in a given period. Finite number of minima, or maxima in a given period. All right. So we have further simplification of this. If f of x is an odd function, that is f of negative x equal to negative f of x, then we have to only, the coefficient a0 and an, they are 0. Okay, all you have to calculate is the coefficient bn. Right? If f of x is even, okay, then bn is 0. So you have to calculate only the Fourier coefficients a, 0, and an. Okay, so those are simplification, but if you're not able to classify as even or odd, then we have to calculate both ans and bns. If it is very simple to classify, you look at the function. If it is satisfying that, of course we know it will have only sign kind of series, right? It's an odd function, so you already know you have to calculate this coefficient. If the function is an even function, it will be like a cosine function. So the coefficient bn is exactly equal to 0. So that's the only Fourier coefficient you have to calculate. Is that clear? All right. All right. So since we have this, if you have to calculate, let us say, coefficient bn, you have to extract it. That's what I was trying to do last time. And so supposing I multiply the equation by right-hand side and left-hand side by sine of 2 pi mx over L, and integrate the function over a period. L here is the period of the function. All right. So if you multiply by that and integrate over a period, f of x sine of 2 pi mx over L dx, what happens? All right, so all I did was, this is your Fourier series expansion for a function which is periodic. And the periodicity of the function is repeat, periodicity length or repeat length is L. That is the expression. And I want to calculate the coefficients an and bn, because that's what we will have to do in most of the PDE problems, the last coefficient that we may have to get it. So what's happening here? What is the first step? What's the second term?
It's 0 unless n equals n.
The second term is 0 because it's an odd function, right? I mean, sine, if you multiply by 2 divided by 2 is sine 2x, you know, whatever, that kind of a thing, right? For it will be like something of that nature, okay. So that is 0. That's an odd function over a period. Okay, sine times cosine, that's 0. What about the first term? That is cosine, right? What a minus cosine 2 pi mx and some coefficient. But over a period, that's also 0, right? Upper limit and lower limit, you have the same value, right? It's just 1, 1. So this is also 0. So you're left with that. So you can, by multiplying by that, you can calculate this coefficient Bn. But what is this quantity? It looks like almost like 2 sine A sine B kind of thing, right? So you can write it as cosine of A minus B minus cosine of A plus B over 2, right? And again, cosine of A plus B, whatever the term, n plus m integral over one period will be 0, okay? The only time it will survive is when cosine of integral cosine of A minus B, which is in this case 2 pi over L minus n, right? Some n minus m term, that will survive when n equal to m because cosine 0 is 1, right? So that will give you what? That integral, what will it give you then? So these are orthogonal functions, basically, right? Now you have something like this. For n not equal to m, okay, let's say it's 0. Always 0. And when n equal to m, what happens? Multiply by 2 and divide by 2, right? 2 sine A sine B, which is cosine of A minus B minus cosine of A plus B. The contribution comes from when these arguments are exactly the same, n equal to n. So when that happens, it is 0, right? Is this clear? So if I have to expand this is nothing but cosine of what? I'm just going to write it once in full, okay? But you understand this. Okay, this is cosine of A minus B, right? I think there's a negative, I think. So negative cosine of A plus B, okay, that term, 0 to L. Okay, similar term, but it is plus, okay? But that will always be 0, okay, because over one period. This will contribute only when n equal to m. It is also 0 otherwise. When n equal to m, cosine of 0 is 1. So this is nothing but all these things divided by 2 is there, right? 1 over half, because that is sine A sine B is there. So this integral is nothing but L over 2. Okay, it's going to contribute when this is, n is, the arguments are the same. So that is 1. So integral of dx is L. And basically all we have done is this exploited this trigonometrical property. So sine A sine B is this divided by 2, that's where the 2 factors coming from. And this contribution over one period when you integrate cosine, it contributes only when these two arguments are exactly the same. So we can always write such thing as whatever is the integration L over 2, right, covers for n equal to m, n not equal to m, so we can write it like that. So those are orthogonal functions. Whereas 0 to L, something like this, cosine of 2 pi m x over L dx is always 0. So this term becomes what? What does that become? Can we write this as L over 2 Bm n equal to m, right? So this is nothing but L over 2 Bm, because the summation we can drop because the direct delta function. So the coefficient n has to become m, n equal to m. So what we have obtained is then expression for these other terms are 0. So I have the coefficient Bm, which I want to calculate in this Fourier series expansion. The coefficient Bm is nothing but 2 over L, 0 to L, f of x sine 2 pi, because it's m now, it's 2mx over L dx. So that is this Fourier coefficient. Alright. So can you now guess what is the Fourier coefficient? Can you use the same process to get coefficient an? What will you do to extract the coefficient a sub n? To get Bn, we multiply this by sine of 2 pi mx L and then integrated over one period. Okay. To get a sub n, what can we do? You have these properties here. Maybe we have to add one more. What is that integral? Right? I put 2 already, so I got 2 here, so. Cosine A cosine B minus sine A sine B plus cosine A cosine B, right away, or that is plus sine, yeah, okay. You just expand the cosine expression. So what should I do then? So you know that property, so what should I have to calculate this, of course. So I want to expand this, let us say, over one period, right, in this case.
Only survives when, only the first term survives when A and B are equal?
Yeah, there's one exception here, that's what I want you to a little bit more focus. Okay, let's consider the case n equal to m, okay? So n equal to m is similar to whatever we had, right, previously, L over 2. Okay, but if n equal to m, but it's also equal to 0, what happens? N equal to m, but not equal to 0, then this is fine. N equal to m, but each one is equal to 0.
Other than L?
It's L. So the orthogonal relationship here is the following, that we have it as L for n equal to m equal to 0, equal to L over 2 for n equal to m, but it's not equal to 0, okay? and of course it's 0 when n is not equal to n. So in this case, we have got you know, these three situations. All right. All right, so if I multiply by now this expression by cosine of 2 pi mx over L dx, we have a0 over 2, 0 to L, cosine of 2 pi mx over L dx, plus a sub n going from 1 to infinity of 0 to L of cosine of 2 pi mx over L, cosine of 2 pi mx over L dx, all right, plus dn n going from 1 to infinity of 0 to L of sine 2 pi mx over L, cosine of 2 pi mx over L dx. So this is 0 because this is an odd function, right? I mean, that's orthogonal functions, right? I mean, so because of that, that term is 0. And this is also 0, right? And then this is equal to, you know, we will say L for n not equal to m, right? This is the case we are going to be doing. So that is equal to L over 2 times am. Okay, so we have an expression for a sub m now, which is nothing but 2 over L, 0 to L, f of x, cosine of 2 pi mx over L dx. So that is your Fourier coefficient. That's how you evaluate that. All right, so they're all coming from these orthogonal property of sine and cosine, that's it. Okay, I mean, it's whatever it is, it's half the period, or whatever, you know, half the integration interval, right? I mean, in this case, but it is coming from basically this kind of property. All right, so we have that. What about A0? So you can just integrate this over period 0 to L fx dx, okay? So you will get a factor of L here, okay? And the rest will all be 0 because integration of cosine over one period will be 0, integration of sine over one period will be 0. So that is the expression for A0, okay? So A0 is here, and this is there, and so when a function is even, that means I have to calculate both A0 and AN, right? Using these formula. When its function is odd, all I have to calculate is just Bn, right? So remember that you have two terms, two Fourier coefficients to calculate when the function is even. So when you do problems like vibration of a string and all that, you have to calculate the last Fourier coefficient in your PD problem from, Fourier series method, so you need to know this. Okay. Let's do an example maybe. This is a very typical problem in Fourier series. Supposing I have a function f of t, it has a value +1 and -1. So f of t is +1. Let's call this as minus t over 2 plus t over 2. So when we say integration over one period, you can change, you can just really take any location. You can go from 0 to t, okay? You don't have to, so it's always, it could be minus L over 2 to L plus L over 2 or 0 to L, doesn't matter, okay? Or L to 2L, it is periodic, right? If it's periodic in the entire regime, you can choose whatever. Although we've chosen like this, sometimes people choose it symmetrically so that the total period is L, that's all matters. So f of t is, okay, -1 for minus t over 2. Right, that's what I had made mistake. Let's get it brought down. The function that I want to integrate is the following. F of t is -1 for minus t over 2 less than t less than 0 minus epsilon, okay? Because there's a jump. And f of t is +1 for 0 plus epsilon less than t. So there's a jump at t equal to 0, right? So the function is negative in this regime, minus t over 2 to this, and is positive 0 to, so there's a discontinuity at okay. So this value is -1, so that is +1. All right. So although the function is discontinuous, we are still, it's only one discontinuity in this function. There aren't many discontinuity within one period. So the period here is L is equal to t, right? Because this is the region, so L equal to t in this case. And we're going to give the Fourier series representation. Now, first, is an odd function or even function?
It's like an odd function.
It's not function, right? It's changing sign. Okay, so we have to only calculate the coefficient Bn here. So what we have to calculate B sub n. B sub n is given by 2 over, the period is t, right? Now, because it's an odd function, you know, I will split the integral into 2 parts because it's got different values, right? I mean, so we have to say minus t over 2 to 0. F of t in this case is, I'm going to write f of t, I'll put the value eventually, sine of 2 pi n over t, the variable is here t, dt, right? Plus, sorry. All right, plus 0 to t over 2, and in that region, the function is plus 1, right? This is plus 1. F of t sine of 2 pi n t over t dt. Right? I have to split because the value of the function is not the same. So here it is -1, right? In this regime, f of t is plus 1. All right. So you can just then write 2 over t minus t over 2, 0, negative sine. I'm going to call this function as omega n, just to make it to make the integration easier. Is 2 pi n over t. Let me call this just for, you know, I can integrate it easier. Plus 1 sine of omega n t dt. All right. So here, you know, you change the variable t to, let's say, negative t prime. Because what I'm going to do is absorb this minus sign inside, okay? Or you can say minus t is t prime, doesn't matter. dt is negative dt prime, okay? And so what's the purpose of that? If I do that, what happens is this whole integral I can now write down as what? 2 times, becomes 2 times 0 to t half sine of omega nt dt. Right? Because I have to change the limits also, right? When you change the variable t to t prime. And then dt will give me another negative sign, and so you can flip the upper and lower limits, so it will be exactly like the other integral. Okay, so don't blindly do it because I mean you have to see it's really the function has a different value, so don't automatically make it as twice. Just check first. Okay, so you can say okay, it's an odd function. That's a negative, so maybe you can, you know, multiply, make it as a even function, but that's not the case. But do it this way. This is the real function. All right. So I have this as 4 over t. So this is my coefficient b sub n. All right. So what is that? So b sub n is nothing but, I have a minus sign, right? Minus sine 4 over t cosine of omega nt divided by 1 over omega n evaluated between 0 and t half. Is this right? Okay, there's a negative sign because integral of sign will give a negative sign, and I have 1 over omega n. So what happens to this? Now I can start steps for omega n. So the coefficient Bn is the coefficient Bn is nothing but 4 over p, the negative sign is there, and 1 over omega n is 2 pi n times t, okay? Cosine of omega n is 2 pi n over t times, so now t is what? T is t over 2, right? And then minus 1. Is that correct? Yeah. So I can cancel this, cancel that. Okay. So the coefficient b sub n is nothing but t and t can also be cancelling. So I can have minus 2 over n pi minus 1 over n minus 1. So this contributes only when n is equal to odd, right? It is the coefficient Bn is equal to 0, then n is equal to, then n is even. Right? So the coefficient Bn is nothing but, there's a negative sign, so it becomes 4 over n pi, then n is odd, 0, then n is even. Alright. Is this clear? Okay, so now, so the Fourier series expansion of the function, the square wave is then nothing but the following. Was it this? Omega n was that, right? Alright. The Fourier series expansion of the square wave is then nothing but summation Bn sine 2 pi n t over t, right? This is what we are writing. So if you expand this out, so B2, B4 are all 0, right? I mean, B2, B4, etc. Even coefficients are all 0. So the first term would be B1 is n equal to 1. So 4 over pi sine 2 pi over t is omega t. Okay, that's the first term. Right, plus the second term will be now 4 over n equal to 3 is the next one, so you contribute, right? With n equal to 3, 2 will be 0. Sine of n equal to 3 will be 3 omega t, and so on and so forth. So this is the Fourier series expansion of this function f of t. So this is really repeating, right? It's a periodic function, so really it's going on like that. So it has got only the odd harmonics in the expansion of this Fourier series expansion. Okay, you come across these things in most electric circuits and electrical circuits, so for me now. So yeah. So what happens at, this is a Fourier series expansion. T equal to 0, what happens? Function is 0, right? And what did I say? At the point of discontinuity, the function should be average of what are the values it was away from it. So it faithfully represents at x equal to, where it is a discontinued point, in this case it's 0, the value of the function is 0. And so the Fourier series representation gives you the correct value at the discontinuity point, right? I mean, of course here it's going to be a combination of sine, it will be oscillating around whatever the value is. It's not going to be, because it is a combination of sine and cosine, except you don't want this to be a big oscillation because it's not one, okay? So it is going to be oscillating close to that value. Right? Okay, so that is the Fourier series representation. What's the time? Just right.
No.
Definitely. Okay.
We tried fixing that actually last.
Yeah, how the one they don't work.
We even replaced the battery and,
Battery has not been replaced. It's been replaced.
well, we replaced it and then we fixed the time, but it's still.
That's what happens to buy cheap stuff here.
I have a question. Is it
Yeah.
a valid approach to have a function and shift it along its period until it's either odd or even, to just only have to deal with half of the coefficients and then just shift it back, or is that not allowed?
What do you see?
So like a periodic function, there's going to be a point in the symmetry in which it's either odd or even. So if we have our period and then we just take our integrals from the center, or we recenter it with a shift, we could then automatically blow away A0 and AM.
But then that's, okay. This is perhaps what perhaps I should emphasize. Whatever this expression I gave is valid, that representation for the infinite domain, right? Or if you did something like that, it may be okay for a small section. You understand? I don't think it's a faithful representation for an infinite domain. Because you have, So the goal is to represent any function with respect to sine and cosine in an infinite domain. N is going from 1 to infinity, right? So this is what I'm going to say. Even for non-periodic function, although we are hooking up, let us say I had something like this, you're given some function. It's not periodic. But if I want to write the Fourier series expansion, I may put something like this and say, okay, maybe this is my period, this is repeating, right? Like that, okay. So, I'll construct the Fourier series for that, and then make the function, whatever is the value of the representative function in this domain. But is this true for any domain? No, it is not. The representation is valid. It has limited, value in terms of, the region in which you can write it in terms of sine and cosine. So that's what will happen, I think, in this case. Okay, so it is. It is a function it is not truly even or odd, right? When we write some other function, it's truly, definitely odd or even in the entire domain. You are just forcing it to be odd or even only in a certain domain by shifting the origin. So it cannot represent the function faithfully for the entire domain. Right? So when I say a function odd or even, it has to be true, the entire domain. So in general, it will be a combination of sine and cosine. It is only when the function is truly even or odd, yes, you can blow off one of the coefficients. Okay. All right. So let us do an example like this. As I said, as a user, you can decide whether you want to make it even or odd. Okay. So I could have constructed the function. So this is again a case where I'm cooking up, right? As a user, I'm just putting these appendages to my original function, and try to do it. And of course, I'll try to make it as in a odd function because I want to calculate only one coefficient bn. I don't want to calculate an and a0, right? So I want to make my job easier. So if you have the choice, you will make it like this because you want to make it. But both of them should give you the representation in terms of sine and cosine that you get will be correct only in a short domain. That's it. It's not, whatever you're representing is not going to be true for the entire domain. That is the difference. Okay. Okay, let me just quickly do this and then maybe do complex series also because I need to. Okay, so you're given a function f of x equal to x squared. So for x equal to 2 is going to be 4 and stuff like that, right? And so we know how this function will behave, so that's all you're given, right? And you're asked to write the Fourier series representation. So, okay, maybe it looks like a parabola, let's say if I did this, okay. Of course you could have done something like that, but I'm just saying if I construct a parabola and forced it to be periodic, right? I mean, right. So I want to get. So if I'm going to represent a function in this 0 to 2, but I have cooked up a function which has a periodicity of 4, right? L is equal to 4. So you will have to, in this case, we are writing x squared in terms of some, sine and cosine function, right? That's what we are trying to do. So in this case, of course, you will calculate a0, and you have to calculate the coefficient a sub n, which is 2 over L 0 to, sorry, minus 2 to plus 2. That's a domain. Function is x squared. Cosine of 2 pi n x over L dx. Alright. So you can integrate this by parts and calculate that. And a0 is f of x dx. So you get a0 and an, and then you can write x squared as we have to calculate these coefficients. Don't forget that we have to divide by 2. Okay, it's just not a0, but I have to divide by 2 also. N going from 1 to infinity, a sub n, cosine of 2 pi n x over L. That will be the expression. But so can you calculate the coefficients, please? What is a sub n? What is a0? That's the simplest one. X cube over 3, negative 2 to plus 2, right? So that is what, 8, right? 2 cube. 8 minus, again, same thing, right? So 16 over 3, is that right? Okay, so that's 16 over 3, which divided by 2 is 4 over 3. Let's see. Okay, that's the first term. What about a sub n? Oh, there's a L also, right? 1 over L is there, I mean, in the expression, is it, 1 over L is also there, am I right? In the formula, did you have, yeah, oh, sorry, 2 over L is there. I forgot to put 2 over L. So it's 8 over 3. 8 over 3. So this will become 4 over, is that right? Did we have it correctly previously? 2 over L, x squared. Okay, so it's x cubed over 3 and there's a half outside. This was 16, right? 16 over 3 and then I have a half, right? 8 over 3 and divided by, okay, I have already corrected perhaps already, yeah. Okay, a over 2, so it's 4 over 3, okay. What about a sub n? You'd integrate that by parts 2 times, not once, 2 times. Let's get this first down, right? Y n x over 2 would be 2 over n pi, okay, sine of n pi x over 2, and then I have x squared definitely. So I have this term first between -2 and +2. And then minus, I should take this inside already. Okay, let me take the half. Okay, let me take it later. Okay, so minus 2 over n pi. This term you can n sine n pi x over 2, 2x dx. There's a half factor, it's common. What happens to the first term? Yeah, maybe you can even simplify this term because this is even function, right? So I could make it 2 times 0 to 2 rather minus 2 to with the sum. So this, then I don't have to carry this half factor. So I can calculate, I could write it like this, 0 to 2 x squared cosine of y n x over 2 dx. Okay, so that makes our life look easier. We can do that way too, no problem, but this I don't worry about. So it's, it's 0 the first term. I mean, for the denominator, because of this factor, x squared is still there, and the numerator sin and pi will be 0. But this term doesn't contribute. Okay, so this you have to do integrate by parts again. What do you get? Again, let me just take 2 over n pi. This is sine, so I get a negative sign, right? So I can put a plus 2 over n pi. I get a cosine of n pi x over 2, evaluate between 0 and, so 2x is also there. Alright, minus, alright, all these things, minus 0 to 0, 4 over n squared pi squared of 2 times,
2 cosine.
yeah, 2 I'm going to take it out, okay, 8, let's take that. Cosine of n pi x over 2 dx. So what happens to the second term? Is it contributing? I mean, that term, I mean, you have cosine of n pi, okay, which is, okay. Another one is minus, oh, we are integrating that, right? So we will have sine, so it will not contribute, okay? Yeah, it will not contribute, that is gone, okay. That will not contribute. And here, the lower limit will not contribute because I still have here x. So I have contribution only from the top, okay? So a sub n is nothing but 4 over n square pi square. I can put 8 because I think I can add it here. 8. Then what do you have? Cosine of n pi, right? So I have a minus 1 to both n. So I have 8 over n square pi square negative 1 to power n. Yes. So this X representation is correct only for this domain, okay? I mean, this is what I want to emphasize. It's not valid from minus infinity to plus infinity, okay? So that representation, Fourier series representation in terms of sine, cosine that I've given is only valid for that, okay? All right. I just want to talk about something which is which will lead to the next topic of Fourier transform. So I think this is important. So whatever we wrote in terms of real coefficients, we can write it in a concise notation. F of x, you don't have to calculate a and b and all that. One coefficient, which is another complex Fourier coefficient, C1, exponential of pi, 2 pi n x over L, and n now goes from negative infinity to plus infinity. So this one is nothing but complex Fourier coefficient. And if you have to calculate that coefficient, C sub n is nothing but 1 over L very simple. Right. All I have to do is multiply by exponential I 2 pi mxl, right? And the same thing, same property like 0 to L exponential I 2 pi nx exponential negative 2 pi mx L dx is 1 only when n is not equal to 1 over n is also there, let us say. Not equal to n. Alright. So we had just Auton property of this exponential. We had sine and cosine previously, but we are exploiting that property, right? Or you can just put it, if you didn't have it, it should be L. It be L. If you want to write it this way, the same way notation we did, then that is analytical way. Now this exactly, it has to be nothing but cosine and sine. So these Fourier coefficients should be related to our ANs and BNs, right? I mean, previously had sine and cosine, and you can check this. I have checked this; they're correct. It's a complex number, complex Fourier coefficient. So it's AN minus IBN over 2, and C minus N is AN plus IBN. These are the Fourier coefficient corresponding to cosine, sine that we had, which is same as Cn star, the complex conjugate. So the main difference is one thing is now this has gone from minus infinity to plus infinity. You can see that, right? I mean, so that's the previously we were sine was 1 to infinity, cosine was 1 to infinity, all that. So in getting these coefficients, you have to now split. The way to do that is I had done it. What you have to do is split this integral to minus infinity to minus 1, and C0 should be equal to A0 and 1 to infinity, and compare the real parts and imaginary parts. This is what you get. Okay, it's a little bit of algebra, but you can check it. It's correct. Now, what is the importance of this? Why this complex Fourier series in this notation is important? Because it tells me something about Fourier transform, right? Fourier series is possible if a function is periodic. If a function is not periodic, right? What does that mean at all in any domain? Whatever. What mean? L is going to be infinity, right? You put L equal to infinity means it's not periodic. Okay. So that's where the Fourier series representation, the summation can become integration. So that's how the Fourier transform representation of a function which is not periodic comes from. So this complex Fourier series is important because it leads to the Fourier transform representation. Okay, so that is an important thing, and for us it's easy because you have to calculate only one coefficient now, right? I mean it's just that, and so whatever it is, it's f of x integral over one period, and it is just changing the sign, and that sign is that's also because of that property, because I need to extract the coefficient, so I multiply the exponential minus 2 pi mx over L, that, and use that kind of a property, and you get it, right? I mean, all right. So I want to talk about one thing, which is also another important thing which comes in many of these transform theories. What it tells you is the average value of the function over a period the square modulus of square of the function, okay, the modulus square of the function over one period is nothing but sum of the Fourier coefficient square minus infinity to plus infinity. Okay, so this really means nothing but average, right? We are dividing by the period, right? So it's average value of is given by that. And if you want to write it in terms of the real coefficient, because Cn is An plus IBN over 2, right? So this is nothing but ANR squared over 4 plus so So these are same, okay, this is same as that. If you wanted to write it in terms of the so for the, this is why we had this condition. For the Fourier series to exist, right? We said, remember the integral of this integrated over has to converge. What does that mean? These Cn coefficients have to converge in this infinite series. If it blows off, then it cannot. Okay, so in that sense, it gives that connection. You know, we see it in terms of this function, but the condition, dirichlet condition, is sort of coming from here. If you think of this, right? I mean, because we represent the Fourier series in terms of these Fourier coefficients and the sine and cosine. So these Fourier coefficients have to be behaving in a certain way. That's what it is sort of implying, how it should behave, because if something, you know, if it's not converging as a function of n, of course, then you cannot represent for that function a Fourier series. Okay, so there are some deep meaning attached to this, you know, this relationship. And Dirichlet had said something integral of this f of x or f of x squared dx has to be bounded. Okay, I mean that was the condition he had given, and that's also coming from this particular theorem, which you can we can check, because you can you take the square modulus of this, right? It's not nothing, but it is it's easy to do that integral where it's coming from, right? You just take the integral of that integral and then give you that. Okay, so this one, because f of f star x, take it and integrate between 0 to L, right? That's what it, then you can extract modulus of Cn squared, right? So the Parseval theorem is coming from this indirectly. You don't have to do much. And I think Dirichlet condition is embedded in this relationship somewhere. Okay. All right, so we'll start next time from here, because what we have given, I've given you is a complex Fourier series representation of a function. So we start looking at, you know, what is Fourier transform, inverse transform, and all that. It will come in quantum mechanics quite often. So that's what we will do. And I'll give you some homework problems based on complex Fourier series. I didn't want to do it, but how to get the complex, you have to calculate only that. The only difference is this, right? I mean, it's not 1 to infinity, making sure, and the definition of Fourier coefficient, complex Fourier coefficient is this. Okay, so it's fairly simple integral, so you can do that. So you can use this, or in terms of sine and cosine, Fourier series representation, whatever you want to do, it is fine. And here I don't even worry about is it even or nothing, right? You just go and blindly do it, you'll get the result, right? Okay, so just to wrap up everything so that you can look at these now, I mean, more confidently, at least in Cartesian coordinates. So I'll give you some problems on this and Fourier series. So there are homework problems, so that
After the test, though, right?
Hmm?
After the test or today?
I'm going to give you today. You can do it, you know. Yeah, the test on Tuesday, but yeah.
So will this be on the test?
So I want the PDE in Cartesian coordinates to be on the test, because we did the PDEs already in the beginning of the class. It's not a new concept for you, right? We already did it, right? So we did all the separation variables vector and all that, we've done it. So for the test, what you have to study is, what is it, start from, we did the derivative method, and then hypergeometric and contingent hypergeometric functions, right? Because that's a very general representation of all special functions. Sturm Liouville expression, how to convert a differential equation into Sturm Liouville form, because that's important. Formula, the Hawthorne excitation property and all that. And then, of course, inhomogeneous differential equation. You have to know both the Green's function method, right? The one based on eigenfunction method, the other one is matching the property of the Green's function, right? And the derivative, right? I mean, so that's it. And then PDE, I think you've already done it. So I think just the Cartesian, don't worry about the Bessel differential equation at this point.
So, you want us to worry about the, doing PDEs and cylindrical coordinates?
No,
Like-
that's what I'm saying. Forget
okay,
about,
okay,
yeah.
Only Cartesian.
Only Cartesian, okay, yeah.
Thank you.
Cylindrical, I don't think It's going to be
Yes.
easy. So, yeah, because Cartesian coordinates we have done, beginning of
Right,
the class we did it, beginning of the session we did it. And you know how to, yeah, so we've already done that. But, so if I'll give homework problem just to practice, and you don't have to return it, but it's just for you to practice, that's why I give homework, so. Because you know what to do, or how to handle that. All right, so you're going to the lecture, we should be moving.